Today we have to discuss about the conductance measurement and its application. Conductance measurement is already completed in one of the previous class. It can be done using conductivity cell. Today we are mainly concentrating on the applications. First one is conductometric titration and second one is precipitation titration, or in other terms, conductometric titration we can classify for acid alkali titration and precipitation titration. That is better explanation. Usually in a volumetric analysis we are determining the endpoint of titration using suitable indicators. But here we are not intent to use any indicator for determining the endpoint. Instead, we are actually measuring the variation in the conductance on the addition of one reagent to other. By studying the variation in the conductance, it is possible to determine the endpoint graphically. This process, I mean conductometric titration, purely based on the number of ions and mobility of ions. When the number of ion increases, conductance increases. When number of ion decreases, conductance decreases. When mobility of the ion increases, or when highly mobile ions are available, conductance increases. Here we have to draw a graph between volume of the titrant against conductance. Depending on the shape of the graph, we can find endpoint. Different kinds of graph can be expected depending on the nature of the solution with us. Among the conductometric titration, we have acid alkali titration at first. We are now start with acid alkali titration. These titrations can be of four kinds: strong acid versus strong base, weak acid strong base, strong acid weak base, and weak acid weak base. These are four possible acid alkali titrations. In Ostwald theory of acid base indicators, you have studied the possibility of first three reactions. In first reaction, phenolphthalein and methyl orange both are possible. In second reaction, phenolphthalein is the only possible indicator in that pH range. And in third case, better one is methyl orange. Phenolphthalein is not suitable to that titration, and there is no proper indicator for weak acid weak base titration. But that titration is also possible in conductometric titration. That is one of the merit of conductometric titration over our normal methods. So, first we have to see strong acid, strong base titration. Example, HCl versus NaOH. HCl is a strong acid and NaOH is a strong base. Equation: HCl plus NaOH gives NaCl plus H2O. HCl is strong acid, strong electrolyte. NaOH is also strong base, at the same time strong electrolyte. NaCl is a salt which is again strong electrolyte, but H2O is weak or feebly ionized. So it is unionized, and other three are in ionized form. We have written in ionic form. Normally, we have a conductivity cell in which we have to take the HCl solution, acid solution. This acid solution titrated against NaOH, strong alkali from a burette. Initially in this container we have only HCl, which is a strong electrolyte. And HCl contain fast moving H plus ions. Because of the fast moving H plus ions, the conductivity of HCl solution is found to be very high. When NaOH is added to this HCl solution from here to this container, the H plus ions present in solution combine with the OH minus ions in NaOH and form unionized water. That means, as the reaction proceeds, fast moving, highly mobile H plus ions are converted to unionized H2O. Then slowly concentration of H plus decreases, and instead of H plus we are getting Na plus in the solution. This Na plus is big in size and its mobility is very low. So we can say that fast moving H plus ions are replaced by slow moving Na plus ions. Then gradually conductivity of the solution decreases up to the end point. Suppose you have been provided with 50 ml of 0.1 molar HCl in the beaker. 50 ml of 0.1 molar HCl in the beaker, and in burette you have 0.1 molar NaOH. Then we can clearly say that 50 ml of 0.1 molar HCl can be completely neutralized by 50 ml of 0.1 molar NaOH. So we have 0.1 molar NaOH in burette and 50 ml HCl in the conductivity cell. When we add NaOH to this solution, fast moving H plus ions here, fast moving H plus ions in the solution are replaced by slow moving Na plus ions. H plus and OH minus ions have high mobility and they can conduct to greater extent. In NaOH we have OH minus. That's okay, but that OH minus is also the part of unionized water. So fast moving H plus ions are removed and slow moving Na plus ions coming to the solution. Then slowly the conductance decreases. Conductance of the solution decreases. And we are adding 10 ml. Then here it is the value. We are adding 10 more ml. That means 20 ml of NaOH is added. Then again conductance decreases. Then 30 ml, 40 ml, and it continues. And finally, at some times, HCl is completely neutralized. Completely neutralized. Then there is no more HCl is present in conductivity cell. As here is no indicator and there is no color change, we never know that the endpoint is over. We will add an extra drop of NaOH. After the completion of the neutralization, we are again adding NaOH. Then in solution we don't have HCl because HCl is already completely neutralized by NaOH. When extra NaOH come to the solution after the endpoint, solution become rich in NaOH. In NaOH, OH minus is fast moving and highly conducting. That means on addition of NaOH after the endpoint, after the equal endpoint, concentration of OH minus slowly increases, which has high mobility and conductance. Then conductance also increases. So in the first half, conductance decreases. In second half, conductance increases. This kind of two lines we have obtained. In between these two lines, we have our endpoint. How to find it? You have to extrapolate this line and this line at the junction of intersection of two liquids. So two lines. Here you have endpoint. We have volume of NaOH, conductance here, and here we will get the value 50 ml of NaOH. So at just 50 ml of NaOH, we will get the endpoint. This is the titration of strong acid against strong base. I think you can understand it clearly by comparing three ions, H plus, Na plus, OH minus. In initial solution, that means HCl, we have H plus having high conductivity, that is slowly removed by NaOH. With decreasing H plus, conductivity decreases. After the endpoint, there is no H plus, but instead concentration of OH minus increases by excess of NaOH. Then conductance increases. Midway between these two lines, we have a intersection, and at that point we will get endpoint. This is the graphical way of determining the endpoint of conductometric titration. In first case, strong acid against strong base. Now we are coming to weak acid against strong base. What's the example? In weak acid, strong base titration, we have acetic acid as weak acid and NaOH as strong base. Equation CH3COOH plus NaOH gives CH3CONA plus H2O. CH3COOH is a weak electrolyte, though, so we don't have a dissociated or ionized form. Here we have ionized form because of its high conductivity and it is a strong electrolyte. Being a salt, it is a strong electrolyte, that is also an ionized form. H2O is in an unionized form. Here weakly ionized acetic acid is present in the conductivity cell, weakly dissociated or weak electrolyte of acetic acid. Here the number of ions are very less. So the solution have low conductance. On the addition of NaOH, CH3COONA, a strong electrolyte is formed. It will dissociate into CH3COO minus and Na plus. Then slowly there is an increase in conductance. Initially there is a small increase in conductance. Volume of NaOH here and conductance here, we will get a slow increase. This process continues until the endpoint. At that endpoint, complete neutralization over. Complete neutralization is over. On further addition of NaOH, excess of NaOH will be in solution. When excess of NaOH is present in solution, free OH minus concentration increases, which has high conductance. After the endpoint, free NaOH will come to the solution, then OH minus concentration increases, which are fast moving, then conductance increases rapidly. These are the two lines. In first half up to the endpoint, this is after the endpoint. Here also you have to take the intersection of two lines. Here you will get the final volume, from which you can calculate the concentration of the solution. Here trend is different. First half slow increase due to the presence of this electrolyte. After that OH minus increases and conductance quickly increases. In third case, we have strong acid against weak base. Strong acid, that's HCl, and NH4OH is our weak base. When HCl is titrated against ammonium hydroxide, the product is NH4Cl and H2O, which is an unionized molecule. Here initially you have only HCl in the solution. HCl contain H plus and Cl minus. Here H plus is fast moving, highly conducting. So due to the presence of large number of H plus ions, solution have higher conductance. When NH4OH is added, H plus ions are removed as water. Then due to the replacement of H plus ions or decrease in concentration of H plus ions, conductance slowly decreases. Here fast moving H plus ions are present in HCl. They are highly conducting. When NH4OH is added, H plus ion concentration decreases, then conductance decreases. Here H plus ions are replaced by slow moving NH4 plus. In first case it was replaced by Na plus. Here it is ammonium. After the end point, at the end point, HCl is completely consumed and there is no more HCl content in the solution. When we are adding extra NH4OH, then solution contain NH4 plus and OH minus. Since ammonium hydroxide is a weak electrolyte, there is no considerable change in the conductance. It will be a constant after the end point. Here also you have two lines. You have to extrapolate it and you will get end point here. You have to notice the nature of graph in each case. We have completed so far the three cases: strong, strong, weak, strong, strong, weak. Now in fourth case, we have weak acid against weak base. That is titration of acetic acid against ammonium hydroxide. Titration of acetic acid against ammonium hydroxide. Equation can be given like this. Both are weak. So in unionized form we have written it. But it is an electrolyte and ionized. But water is unionized. Nature of the graph is an interesting one. This is the nature of graph in the first half. After that, graph will be like this. How to explain these three lines? Initially, conductance of the solution is very low because in the container we have only acetic acid in the solution, which is a weak acid and weak electrolyte, so conductance is very low. Conductance is very low. On the addition of NH4OH, initially decrease in conductance can be seen. Decrease in conductance is observed. How to explain this phenomenon? When ammonium hydroxide is added to acetic acid, ammonium acetate, a strong electrolyte, is formed. When strong electrolyte of ammonium acetate is formed in the reaction medium, this acetate ion develop common ion effect to acetic acid, which you have studied in analytical chemistry. What is common ion effect and how it can be applied in chemical systems. So due to the presence of this ammonium acetate, where acetate is common to acetic acid, then dissociation of acetic acid slowly decreases. That means conductance of solution slowly increases due to the decrease in the number of ions in the acetic acid, as their dissociation is suppressed by this acetate. When excess of NH4OH is added, that is the explanation for this region. Which region? This region. When excess of NH4OH is added to acetic acid, large amount of salt is formed. Then large number of acetate and ammonium ions are formed. Both ions are formed in large excess. Due to the presence of this much of ions in solution, then slowly increases. And finally it reaches to the end point. We don't know where actually the end point is because there is no indicator or color change. And after the end point, without having any idea, we are again adding NH4OH. Then solution become rich in ammonium hydroxide. Instead of acetic acid, solution become excess in ammonium hydroxide. Since ammonium hydroxide is a weak electrolyte, there is no appreciable change in conductance. It will continue as a constant. Here also you can extrapolate and you will get the intersection at this point. At this intersection you will get the volume of alkali or ammonium hydroxide you have used. We have N1, V1 equal to N2, V2. 0.1 molar acetic acid we have initially collected is 25 ml, and to that we have added 22 ml of ammonium hydroxide. Here you have 22 in this point. That 22 you have to put here. Then you will get N2. 0.1 into 25 divided by 22. That is the normality of ammonium hydroxide. From that you can calculate the mass of ammonium hydroxide in a given volume. These are 4 types of acid-base titrations. In conductometric titration we have one more titration, that is precipitation titration. During a precipitation titration, when a precipitate is formed, then the color change of the indicator cannot be observed accurately. So the detection of endpoint is difficult under precipitating condition. So under the precipitation reaction, it is better to measure their conductance instead of using any indicator. You have KCl in the container, and in burette you have AgNO3. When AgNO3 is added to KCl, KCl plus AgNO3 gives KNO3 plus AgCl. Initially, in the solution you have K plus and Cl minus, K plus and Cl minus. On the addition of AgNO3, we will get AgCl, that is a sparingly soluble salt, which is not highly soluble in water, and it remains as insoluble or precipitate. So we don't want to write it as Ag plus and Cl minus. Instead we have to write it as AgCl. When salt dissociate in solution, then only we have ions. Since it is insoluble in water, we don't have any right to write it as Ag plus and Cl minus. So K plus is common in both sides. What actually happens is that Cl minus ion is replaced by NO3 minus. The peculiarity here you have to note down is that speed of Cl minus is same as that of NO3 minus. So when Cl minus is replaced by NO3 minus, there will be no change in conductance because they have same speed and same mobility. So there is no change in the conductance. After the addition of AgNO3, at some points we are coming to the end point and KCl is completely removed from the solution. It becomes KNO3. After the end point, when you are adding AgNO3 solution excess, when after endpoint, if we are adding AgNO3, AgNO3 dissociate in solution and NO3 minus concentration slowly increases. Once again, when AgNO3 is added to the solution after the endpoint, concentration of NO3 minus rapidly increases due to the dissociation of AgNO3. Because of the increase in concentration NO3 minus, conductance quickly increases. Here also you have two lines with different slopes. You have to extrapolate the line and you will get endpoint here. This is precipitation titration. Here we don't want to use any colored indicator. Even if we are using indicator, there will be no chance to note the exact endpoint. Because of the presence of precipitate, color change will not be very clear. Now what are the applications of conductance measurement or conductivity measurement or conductometric titration? In conductometric titration, we have discussed acid alkali titration or neutralization reaction. That is the another word of acid alkali titration. And secondly, precipitation titration. First application is that titration of colored solution can be done here. If solution itself is colored, how to use an indicator? Color of the indicator will merge with the color of the solution and they will change into another color which will not be visible at the endpoint clearly. Second one is they can be used in very dilute solution. First one is, in the case of titration of colored solution, it is better to employ conductance measurement instead of normal indicators. Very dilute solution can also be verified in this method. And third one is, there is no proper indicator is available for weak acid weak base titration. That reaction is also possible here. Precipitation reaction cannot be conducted using indicators. That is also possible using conductance measurement. Most important one is no special attention is needed. No special attention is needed at the endpoint because we are determining it graphically, not from the color change. It is from the graph we are getting the endpoint. So you can add the solution continuously. At some point automatically line will shift to here. From this two line we will get the endpoint. So there is no proper care. There is no need of proper care while doing the experiment. So we don't have to be much bothered about the endpoint while doing the experiment. Definitely the endpoint will get from the graph without any error. These are the applications of conductometric titrations. With this, we come to the end of electrochemistry 1. Thank you.